to all of you. So today we are going to talk about. Uh, so we have just learned about magnetism, ferromagnetism, ferrimagnetism. In a similar way, there are behavior that we'll find like so parallel to ferromagnetism. You have also electrical uh, behavior that is called ferroelectric. Then there is something called piezoelectrics. Dielectric you are already familiar with, the term dielectric constant. So we'll take that concept at a more fundamental level, try to understand that. So these are the so I will just take a preliminary look at all these materials, dielectric, piezoelectric and ferroelectric. So it will just, I won't take a very long, lengthy classes on this, only just to inform you so that you are aware of the things, the basic about all these three types of material we'll try to learn. So you are all also familiar with capacitors. It is a household thing now. Many of the appliances, equipments, fan and everything, कंडेंसर जिसको आप कहते हैं कैपेसिटर होता है कैपेसिटर is a device which is stores is used to store charge. So जो एक बहुत simple view है capacitor का, that is you have two parallel plates A and B which are separated by a distance d, and then you connect the two plates to the terminals of the battery. So this makes your capacitor. So there will be accumulation of charges on each of these plates face to face, separated by a distance, and this is the capacitor. So it is used for. So this is a very uh, initial thing when you start with learning about capacitors. In actual sense, the capacitor is something which is rolled into sheets. The plates that you see here, imagine the plates are not very straight, they are just curved, rolled into multiple layers. So then you have this kind of structure, and this is a most common thing that we usually have in our appliances and in daily life. This is a common kind of capacitor that is used, the B, this one. Okay, so this model is something, so this is a very useful thing. Capacitor as a, it is it stores charge, so it is also an energy device that can release certain burst of uh, electric field sometimes. It is also used in many things like heart defibrillators, so medical science, anything. So everywhere capacitors are there. You find. So what you have essentially is that you have a two parallel plates connected to battery, and the space that you see is actually air, vacuum, or any other insulator. So between two parallel plates, you have to put some gap. The gap that is also defines the thickness of that. So it has to be an insulator of a certain thickness. So that becomes the distance between the two plates. Okay, whether they are standing vertically or they are rolled into sheets like the second picture, both are example of, okay, example of capacitor. So it is the insulator that we put, we do not allow the two parts to touch each other, and we put an insulator in between the two plates to provide separation. So So initially both what you see is uncharged, and after connecting to battery they have the plus q on one plate and minus q on the other plate. That's how the two halves you get oppositely charged. So rolled capacitor, that is the second example. Parallel plate capacitor, that is the first example. So this is the thing that, so when you have this kind of plate, what will happen? You have accumulation of charges, plus charge here, minus here, plus, minus, and there's an array of charges, that is this kind of arrangement of charges like this on the two plates facing each other. So the electric field lines, when you try to draw, it is starting with plus and ending at minus. So minus charge on adjacent plate. So this is how we draw electric field lines. अब तक आपने ये भी नोटिस किया होगा कि इलेक्ट्रिक फील्ड लाइंस और मैग्नेटिक फील्ड लाइंस में जब ड्रॉ करते हैं डिफरेंस है. एक पॉइंट चार्ज अगर जैसे हम Q लेते हैं Q प्लस, इसका इलेक्ट्रिक फील्ड we draw in all directions, right? Electric field, and it is actually, it will somewhere, it will terminate with a माइनस चार्ज कहीं पे होगा तो वहां पे जाके टर्मिनेट करेगा. But whenever you draw a magnetic field, that in previous classes you have been seeing a magnetic, so electric field lines are drawn starting from a source to a sink, source to a sink. So plus and minus, so it originates at plus and ends at minus. But when you have magnetic dipole, magnetic a magnet is drawn, then you always draw it like mm, a snake biting its own tail. So whenever you draw a magnetic field, you always draw lines of forces which are curved, and so this is a difference. Magnetic lines of forces, remember, a snake biting its own tail, that's the thing. Electric lines of forces, whenever you draw, so electric field lines of forces, when you draw it as a starting from plus to end at the negative charge, so anywhere like that. So this is the drawing. So if you have two parallel plates, so the electric lines of forces are straight line originating from one to ending at the other like this. So this is how, and so electric field produced will be proportional to charge that has been accumulated. Electric field produced is proportional to the charge, and you also know that so this the capacitor remains overall neutral, but it has charge Q, that is plus Q and minus Q, both are stored on different uh, two parallel plates. It will amount of charge will depend on various factors, that it depends on the physical characteristics such as size. So actually, if you know from your class 11 12 things, then you must remember that capacitance is epsilon naught A by D, something like this. So this was the, so if it is the, you are putting the plates are in the vacuum, then this is the capacitance is defined as this, the capacity to store charges. Capacitance is the capacity to store charges, and that is given by this in a similar. So this is one of the so dependence on size. So this is the area of the parallel plate. D is the separation, and between the two plates. So that's how we also define capacitance. And in terms of storing charges also, we can see that uh, E is directly proportional to Q. That's what we are writing. So electric field that is produced between the two plates is proportional to Q. So when you write in terms of E, so electric, and you should also know E, voltage, the potential difference that will be produced, V, is given by E into D, the distance. So you can correlate with voltage also, and it turns out to be that Q is proportional to voltage, and you have Q CV. So this is another relation that relates to the potential difference and voltage. So all these things can be related to each other, and a system. So these are two important things. So one related to the size, another related to the thing, and this is capacitance. So storing capacity can be defined in this way. So now if we just look at this, okay, so parallel plate capacitor system that is shown in the slide here, and so the relationship between the voltage and the charge that I just told you. We also see that each electric line's force starts from individual positive charge, ends on the negative one, that's on the other plates, and these are the practical capacitors. Practically, this is what you see in daily life. These are the all different designs of capacitors. So different capacitors will store different amount of energy for the same applied voltage. For the same applied voltage, you can have, so depending on their physical characteristics, so plate area and the distance between the plates, all these things are important. So if you can bring them closer, as close as possible, if the separation is less, then so one thing we have, C is equal to, is proportional to the area, it is proportional to 1 by d. So capacitance is also inversely proportional to distance. So if distance is small, capacity to store charges increases, and if area is more, greater is the area, greater is the ability to store charges. So this is what we mean by saying the physical characteristics. In addition to that, you also have the, whether it's air, vacuum, or some other material between the two plates. The nature that we said that we place, I said that there is an insulator placed between the two, this conducting plates. So that insulator, the nature of insulator will also affect the this thing, the overall capacity of the capacitors. So that is where the material that we place in between, that is also called dielectric. The insulators that we are talking about, kind of insulator that can be placed, they are known as dielectrics. And so major factors, so Q is equal to CV, we know that. So this kind of, so just a simple calculation and you will learn that what is the so if you try to understand capacitance and stored charges, parallel plate capacitor with area of 1 meter square and 1 millimeter. So if you calculate simple this one, what is this? C epsilon naught into a 1 meter square by 1 mm square, so 1 into 10 to the power 3 minus 3 meters, 1 meter square. So this is your almost a very small. So when you have 1 meter square area, and epsilon naught will be 8.85 into 10 to the power minus 12 something. So it will be a very small value that you can store. It's something in micro, um, a very small value that you can store in the. So epsilon naught is actually small value. So you will be able to store a very small value if you just simply calculate this factor. You'll find that 1 farad is a very huge number, and you are when you are making a parallel plate of 1 meter by 1 meter, a huge structure, and then putting just a small distance between them, separation, still you are able to store a very small amount of charge, which may be in the order of very small charges, which is be small enough and corresponding to, sorry, a few nanofarad. That will be the value that, if you calculate it carefully, it will be something around few nanometers, sorry, nanometers, nanofarad. So it is very difficult to store charges. And sorry, where is my slide? So that so that is something that I wanted to highlight, that if you difficulty in storing charges. You cannot design such a big structure when you have to use in small equipment. Uh, so how to, what should be the way out to store more charges on this? So there comes the role of the material that you are placing in between the two things, two plates. Okay, so simply it is not possible to, practically it is difficult to just separate the two, increase the charge, increase the size of the plates, keep the distance small. Still you are not anywhere in a practice store, uh, you are not able to store enough charges for to make any particular device work. So okay, so there is something that we need to do, and there comes the role of certain types of materials to be placed between them. So that is called dielectrics, the materials which are having this property that can, what they do, dielectric material will reduce the electric field. They will, it will reduce the, sorry, it will reduce the overall. So let's see what happens. So there is a difficulty, and this difficult, how to get over with this difficulty of storing large amount of charge in capacitors. We want to make small object, a small device storing large charges, but that is even after 1 meter by 1 meter with 1 mm separation, only few nanofarad capacitance is observed. So how to increase the capacitance, that is the question. And so what should we do? So this insulating material that we are placing, that is the solution. uh, and this, the nature of insulating material that we place, we call them dielectric. When we place them between the two plates, the role they play is that of a dielectric. uh, we uh, we always keep the distance small as possible, and then place this material which which can, so insulators are something that can stay, even if you apply a very large electric field, they will not break down, they will not so so there is a something that we define here. So if you go on increasing the electric field, there is a point beyond which any material can start become a conductor. There will be charges which will be freed up, which will be, because you are applying such a huge force, and every insulator or anything is composed of electrons and protons. So at some point the electrons just ejected out, and that is the breakdown of the system that we call. So that become, any insulating material can become conductor when you apply a very large amount of electric field. So this maximum electric field that can be applied to an insulating material before it begins to conduct. That is called breakdown. That is the point when it becomes conducting. We say that it has broken down, and that maximum electric field is its dielectric strength. So if you just see a few points here, the dielectrics, the different types of dielectric material, insulating material that is to be placed within the capacitor. Vacuum, for reference, we take it as 1. Air is very close to this, and if you have air between two plates, what will be the maximum uh, uh, electric field that you can apply before the air becomes conducting? So that is 3 into 10 to the power 6 volts that you can apply before it becomes conducting, volts per meter. So this is the measure of maximum electric field that can be maximum electric field before that can be applied before it becomes conducting. So so if you have at this particular value, it will become conducting. There will be breakdown, so we call it dielectric breakdown. And this the value of this electric field is called its dielectric strength. So you can see air can easily break down at 3 into 10 to the power 6 volts per meter. If you take some other things, so take a sheet of paper, it is a better material, 3.7 dielectric constant. So this is the relative permittivity that you can say epsilon r, or dielectric constant. It is also sometimes denoted by kappa or epsilon r. These are the two symbols that we assign to dielectric constant, and see its dielectric strength 16 into 10 to the power 6. So as compared to air, you can clearly see that even if you use a sheet of paper between two parallel plates, that is a better situation, and you can have a better capacity to store charges. So you can look at Teflon. The Teflon, it is very high. The value in this chart that you see, 60 into 10 to the power 6. So gradually you are improving the performance of your capacitor. You are able to store more a large amount of charge. The capacity to store charges increases when we have something which can withstand a high electric field. So for Teflon, it can go up to 60 into 10 to the power 6 volts per meter, and still function normally without breaking down. After 60 into 10 to the power 6, at this value or greater than this value, it will become conducting. So Teflon becomes conducting at this value of electric field, which is very high, and so you can use it safely in devices and having greater conductivity. So how does the dielectric increases the capacitance? We should try to learn about this. So this is the structure that you see. So you have plus and minus charges, and suppose you place a molecule which is having dipole moment. It is a polar molecule. Then this kind of arrangement will emerge. You can see plus minus plus minus. So it will be oriented in such a way that the positive end of the dipole is facing the negative plate, and negative end of the dipoles, they are arranged on this side and facing the positive plate. So this is the dielectric that we are talking about. Okay, so polarization of the insulator is how it polarizes, the mechanism of polarization, all these things matter. And so so if it can be easily polarized, it will have a very high dielectric constant. So more easily the polarization occurs, greater is the dielectric constant. So for example, if you have water, it has the dielectric constant of 50. It is already uh, has some polarity. It is the bonds are polar, you know that. It has a net dipole moment, that also we know. And so it is having a polar molecule will be good for this kind of thing. So imagine water molecule is placed and then you have plus minus. So viewing this, we can visualize the water molecule as dipoles, uh, with having plus and minus ends, and then they will be arranged like this as shown in the picture left hand side. And the Coulomb force between the closest ends of the molecule and charge on the plates is attractive. So this is the attractive force plus. So this helps in keeping bringing more and more charges on the negative plate. So you have an arrangement of plus plus plus, the dipole, um, positive ends of the dipole, which are arranged in this manner. They will attract the negative charges, and so they can be hold up. They can be because of the attractive interaction. They will be. They can stay close together. Otherwise, you imagine if there is no such thing to attract these negative charges on this plate, then remember there is repulsion between these charges, minus charges on the plates. So if something in the you have put something in the medium, as a medium in the filling in the empty space, and that in that empty space, this when this material is placed, it it has arrangement of positive charges, positive ends of the dipole in this manner. So it helps in minimizing that repulsion of the negative charges, the electrons that has accumulated on the metallic surface on the other on the plate of capacitor. If in absence of such a material, it will be difficult to once you are stabilizing that effect because of attractive interaction, more and more negative charges can be accumulated on the plates, and so your capacity increases. It's simple. So that's how. So it is this kind of interaction. So if dipole is strong, suppose the molecule that we are using as a insulator, it has a high value of dipole moment, so you can expect that this interaction between the plates and this uh, an array of these dipoles will be much stronger. And so because of the increased interaction, attractive interaction, now some more negative charge can accumulate on the surface of the metal plate. So this is the idea that we take forward. uh, so that there is attraction of the charges on the plate by these water molecules that we are visualizing placed over here. So in a similar way, if we place some other polar molecule which is having greater dipole moment, we can expect a greater attraction, and more charges will accumulate on the opposite charges will accumulate on the surface. Similar argument you can give for the on this other plate. So mutually it will be on both ends, on both sides, you will have accumulation of positive and negative charges, which is represented by plus q and minus q. So instead of having air or vacuum, it is better to put something like this, and that increases your capacity to store charges by several order of magnitude. So this is the interaction. So plus and minus, this is the electric lines of forces that we were drawing earlier. And if you are looking at these dipoles that are arranged, so between them now you can draw like this. So electric lines of forces have been reduced. So wherever you have dipoles, molecules are there, minus and plus. So this is a dipole, this is a dipole here. So this plus and minus that you are seeing is actually this arrangement of dipole from the taken from the previous picture. And so the electric field that you will draw now will be drawn like this, from positive to minus, here ends here. So your electric lines of forces have been shortened. So when you look at the electric field inside the capacitor, so this is the second view that we are taking. So fields lines end on the, so as I told you, when you draw electric field, it is always drawn starting from the plus ending at minus. So arrow is always pointing in that way, in that sense. So now what you find that once you have put molecules like this, like water molecules, which is polar, then field lines end on, there are fewer of them going from one side of the capacitor to the other side. So the line that is going from one extent to other, these are now, such lines would be fewer as compared to the previous case, when there is nothing placed in between them. So wherever dipole will be there, only in empty spaces it will go through, and wherever dipole is present, the lines will become shorter. It will start here and terminate here. So the electric field strength is less now as compared to case of a vacuum. If there were only vacuum between the plates, as compared to that situation, the electric field strength is reduced between the plates, and keeping we have, and still we are able to, even with the same charge on the plates. So the voltage that will develop will be E into D. So even with low voltage you apply, so what is the advantage? Now what you have done, you are applying a smaller voltage V and still getting the same charge Q. So your problem is solved. You are in a position to, so say if we are using water, by 80 times you have increased your capacity, the electric field has decreased by this amount, and at the same time you are able to, so the requirements, so initial requirement to apply the voltage, so you decreases by 80 times, and you have, and you are still getting the same charge Q. So the capacitance is high, the voltage required V is very small, and capacitance increases. So dielectric constant is this, it is also defined as kappa E by E naught. So E naught is the ratio, E naught is the vacuum, electric field in vacuum, and E is the electric field with the that insulating material that we have. So this is related to the polarizability, the dielectric constant that we are talking about here, so this ratio. So it is polarizability of the material that we talked about. So these are the two contrasting things, pictures that we have when you have vacuum and when you have dielectric material placed between them. So what is, so in what you are seeing here, you can also say a dielectric reduces the electric field between the two plates of a capacitor. The role of dielectric is to reduce the electric field. So something, any material that can do this, we call it dielectric material. Okay, so capacitor, so relative permittivity. So there are ways in which you can define this and relate the capacitance with the epsilon, the permittivity, and dielectric constant. So, when the magnitude of external electric field becomes too large, the molecules of the dielectric material start to become ionized. So if the electric field that we apply it becomes too large, then molecules will be ionized, and some of the one or more electrons can be removed from that material. So it becomes free, no longer tightly bound to the molecule or atomic structure. So this is a situation we say that it is dielectric breakdown. At this point, they become conductor. So at any material, any material can become conductor at very high electric field, and that point is called dielectric breakdown. The and the strength of electric field required to do so is the dielectric strength. So the electric field at which the molecules of an insulator become ionized, that is, the electron is now free to remove from the molecular orbitals or atomic orbitals. Now they are free to move about. So that is a situation that we say it has reached the dielectric limit of the dielectric. So that puts a so you can only work within that range of electric field for with a capacitor. So this is a picture which shows dielectric breakdown. So dielectric breakdown is can be when the voltage is applied. So the tree-like branch-like pattern that you see, it is a glass which which can act as dielectric, and it has undergone a very high electric field was applied, and it has shown this kind of pattern, which is a typical, a very beautiful image which shows dielectric breakdown. So branches like tree that you see, so that is representing the breakdown patterns. So dielectric constant, so this is the initial thing. Initially, say water molecules, you have randomly oriented dipoles. Now when you place them between the plates of capacitors, parallel plates, then they will be organized in this manner, and each one will have interaction like this. So this is the parallel plate, and very close to that you have this kind of charges that accumulate. So dielectric polarization, so it is the polarization that is responsible for this kind of behavior, uh, and let's try to understand the dielectric polarization now. So dipole moment, okay. So insulating material can have dipole moments produce polarization due to the polarization of the molecules within them, or if there are already molecules have some dipole moments, there will be alignment of the dipole moments because of the applied electric field. So two things can happen: separation, there will be polarization. If there is no dipole, there will be dipole created. If the dipoles are already there, permanent dipole is there, it will get aligned with the electric field, and so overall resulting in a uh, picture that is shown here. So things will be like this. So dielectric material will respond with a change in the charge distribution will change in the dielectric material as the electric field is applied. So you can have this kind of arrangement. So imagine if you have, so let's take, as we are discussing water molecule, we can take it further. So suppose there are water molecules filled between two plates, and so there will be some of the water molecules which will be in contact with the capacitor plates. So this one, the black ones that you see, these are representing the dipoles, which are, so the molecule, they are dipoles in the molecule, and these molecules are in contact like this, such that the positive end is in contact with minus, and here like this. In between the two, so this, you have inner layer in which they are not so they are just free. The charges are, the dipoles are not tightly bound, but they are rather free. So there are two types of molecules within the dielectric material that you can distinguish. One, between the capacitor plates we have free charges usually floating around in the material, so that is the middle situation. And but although they are aligned, they are free to move around. In contrast, you also have bound charges, so that is the this case, which are in direct contact touching the capacitor plates. Okay, so this is an example of so this will be the response as the electric field changes between the plates. When you apply voltage, when you change the applied voltage with with a battery, this is the response that also affected. And charges in the material will have this kind of response. There will be floating charges inside in the inner area, in the middle portion, whereas at the edges they are in contact with the capacitor plates, and so you have this kind of arrangement. So polarizations are of different types that we can talk about. So if the molecule is neutral, there is no it doesn't have any permanent dipole moment. In that case, so imagine this kind of situation: you have a symmetric distribution of charges, electronic charges. When the electric field is applied, that it gets polarized with so so unpolarized case, the center of positive charge, the center of negative charge, both align here. But here in this case, once you apply the electric field, the center of positive charge is here, center of negative charge is somewhere this side, so you have a net dipole moment produced. So this is the polarization that we talk about. And so there, because of the distortion produced in the electron cloud, there is polarization, and there is dipole moment developed. Then there is another case. So this is the kind of, so this electronic polarization that we just discussed, this is a model that will apply to something like Teflon or something, where you do not have uh, any permanent dipole moment. Okay, orientation polarization applies to the molecules, the material which already have dipoles, and when we place into the electric field, they get move, they just reorient themselves, they will rotate and align with the electric field. So force is QE, that we know, and depending on that you can have alignment. So because of the torque produced, this is the torque. So when you have already have permanent dipole moment in the material, then this situation is applied to, so HCl and H2O that we are discussing, we already have the dipole moment, so there is nothing like inducing a new dipole, creating new dipoles. The dipole will only tend to align themselves, and so between the parallel plates you can imagine how the, if you have HCl, so Cl will be pointing towards the uh, positive plates, and H plus partially charged H atom will be facing the negative, so that will be the tendency. So this is the orientation that will happen, and which was shown in the previous picture, like yeah, here. So nothing, no proper orientation, and then it gets oriented. So this is the case, second case, where we are talking about orientation polarization. So overall net dipole moment will be much more as compared to random ones. It was 0 overall. uh, in the So because of in random, if you have water molecules placed in a container, simple, because of thermal energy, so all will be randomly oriented, and so resulting in there will be net zero dipole moment. But once you place between these two plates, parallel plates of a capacitor, because of the electric field, they will orient themselves and get aligned with the phase. So that is what happens. So these are two pictures. E is equal to 0, net dipole moment 0, but when you apply a magnetic electric field, they will get aligned. So this is what we mean by orientation polarization. And this arrangement that happens can be given by Boltzmann statistics. So the dipole orientation polarizability per molecule is given by alpha p naught square by, so this is the polarization P. So just like we defined magnetization, this P is the summation of di dipole moments, electrical dipole moments, electrical dipole moment over a given volume, or uh, over a given mass, in a given mass of a. So just like we defined magnetization in the case of magnetism, here also we are taking the summation of all the dipole moments, and then assigning a term, giving it a value, giving it a name called polarization. So this PAV is that thing, and P naught is the at a zero temperature, the polarization at 0 Kelvin, and P is the at any temperature you can have it varying. So this polarization P is similar term. Only thing is that we are talking about, instead of magnetic field, so magnetization, उसका parallel में हम term use करते हैं यहाँ पे polarization, a quantity that we use for showing in calculating it. So this is a measurement that is done for when you measure all the magnetic moments summed up together over the entire material. That is a polarization. So this is an important factor, extent of polarization. And then there is also something called ionic polarization. So this is a mechanism for the crystals like NaCl, KCl. So ionic crystals will show this kind of mechanism. When there is no field applied, they are like this. When you apply field, suppose you apply the field in this direction, then you have ions which can slightly move. So you see this location, this ion has moved. The negative charges, they are bigger, they are not able to move that much. So relative positioning of the cations has happened, and some dipole moment has been created now. So uh, so in absence of external field, there is no dipole moment. Okay, no dipole. And here, because of this kind of thing, we have, you can see dipole being developed. Okay, so dipole moment, there is so this is, ion becomes displaced, which leads to an induced polarization. And because of this, so this induced polarization is given by alpha times this local electric field. So E is the local electric field experienced by the pair of ions. So by these three mechanisms you can have the change. So this is how the dielectric materials acts and lowers it, decreases the overall electric field between the two parallel plates. So three mechanisms I told you, and there's also a fourth one, space charge model, interfacial. So as we are talking about the different mechanism, they are for different types of materials, right? So first one was for non-polar, second one was for polar molecules, a material which has already polar molecules are there, that is a permanent dipole is there, and the third one we talked about was for ionic, and fourth one, let's see, interfacial or space charge polarization is a special case when accumulation of charge at an interface between two materials or two regions. So space charge polarization is accumulation of charge at an interface between two materials or between two regions within a material. So this will happen in presence of an electric field. So plus and minus two electrodes and dielectric is placed in between them. So there's accumulation of charges on one end, plus 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 on one side, negative one having this side. So because cations are smaller, if you have something, suppose it's not so solid, and uh, if you have movable charges like positive ions and negative ions which are moved through, then this will happen. Uh, so so this type of polarization is different from orientation or ionic polarization, because instead, so all in all previous cases they were bound positive and negative charges. So it is the so so this is particularly in polycrystalline solids. Interfacial polarization is observed in amorphous or polycrystalline solids. So any free charge can accumulate in a field causing interfacial polarization. Okay, so these are the four different ways where polarization can occur, in which polarization can occur. So moving ahead, we can also, uh, after discussion of dielectric materials, we can talk about piezoelectric. Piezo is the word that comes from French piezo, which means piece. Uh, so when you apply force on this, twist it, you will get some current generated. So piezoelectricity is the term that when you apply a mechanical stress on an object, it will generate voltage potential difference across the two surfaces. So across the two surfaces, it will generate potential difference V, potential difference across the two surface. So basically one becomes positively charged, another becomes negatively charged, and two surface because of this, and then you connect this, it will happen. So initially it is a neutral crystal. When you apply force, so quartz crystal is an example of a piezoelectric crystal, where it is used in watches for the same reason, because it is piezoelectric. So because of the stress produced, it will generate voltage, and that then you can connect it to galvanometer or any bulb, and it will light up. In the reverse thing, a piezoelectric material can also show the opposite effect, that if you apply a source of battery, if you have a source of a current, if you apply a certain potential difference across the crystal, it will show twisting motion. So twisting motion is seen. So vice versa, it is the reverse of the piezoelectric effect, reverse piezoelectric effect. So in this case, when electric field is applied, it will show stress. So it will show twisting. The first one, so it was first compression. So two types of uh, piezoelectric effect is observed. One is compression. So you put a material and compress it. You apply force from both ends, and it will generate some voltage. And then there is tension, that is, you stretch the both surfaces outwards, so there will be increase in volume, and so this kind of thing is piezoelectric. So if the material has same type, so the okay, compression, and so you also see when you are compressing, the voltage developed is plus minus, like here, plus minus, and then you also have the applied voltage has the same polarity as the material expands. If the material voltage has the opposite polarity, then the material contracts. So this is an inverse piezoelectric effect. So this is a concept which is nowadays being used. So even if you use in a kitchen, you are using a lighter. You use lighter. So all there's a piezoelectric crystal even in that. Sugar is also a piezoelectric crystal. Peppermint that you eat, if you crush it between your teeth, you will see a spark. That is due to electric spark that you see. So that happens. There are many YouTube videos available where in dark people crush this large number of Mentos or peppermint, and there's a spark in the mouth. So that is the piezoelectric effect. So it is a very interesting thing, and in their thoughts, research is going on to have something like when you move on the road, because of the pressure, because of the movement, the electricity will be generated if beneath the road you have some piezoelectric materials. So that kind of roads are being made in Israel and many other places, in US, and two places they are doing it. So generating a large amount of having a large amount of piezoelectric material laid along the road, beneath the road rather. And as car moves, as the vehicles move, it because of the pressure, because of the stress, electricity will be produced. So piezoelectric material is so shortening or lengthening. So compression, if say inverse piezoelectric effect is the thing, when you subject it to applied electric field, it will show twisting motion, like shortening and compression and elongation. So this word piezo has originated from Greek piesin, which means to squeeze or press. It was two brothers, Pierre Curie and Jacques Curie, that it was discovered by them in 1880, and still its full potential has not been utilized. For it can be helpful in overcoming the energy crisis. So that's what the point he was making. So in the original work of these Curie brothers, they showed piezoelectric effect in tinfoil, glue, wire, magnets, and a jeweler's saw. So quartz crystal, cane sugar, Rochelle salt, topaz, all of them showed this kind of behavior, that when you apply mechanical stress, it will produce electricity. You can generate potential difference and connect it to a circuit. You will see a current passing, illuminating a bulb. So this was further modified by mathematical explanation of the was given by Lippmann after the experimental discoveries by Curie's. So we are not going to how they are made. Uh, Piezoelectric crystal, typically this is the idea. When you apply force, one surface will generate plus, another surface will generate. So you see the charges O minus, O minus. So you have excess of oxide on one side and Si on the other side that is touching the surface. So this gives you a kind of positive terminal, negative terminal, and then you connect it to a bulb. It will light up. So when you connect it to the two ends, it will show. So displacement of electric charge due to deflection of the lattice in a that's happened in a quartz crystal. So large circle represents silicon atoms while the smaller ones, so this is already shown here. Quartz is one of the most stable piezoelectric materials. So other piezoelectric materials are naturally occurring quartz, also this is already discussed. Bone is also piezoelectric. Man-made gallium orthophosphate, ceramics, titanate. So these kind of materials are polymers, PVDF. So these are the materials which show this kind of property. Typical structure of this is shown. So temperature, so there is a temperature beyond which this will show so piezoelectric effect. Traditional piezoelectric ceramic. So you have cubic lattice of, so this is the situation above Curie point, below the Curie point, and this second picture is for the below the Curie point. And so below the Curie point there is, when you compress or stretch, there is possibility of accumulation in the charges being developed because of this kind of structure, tetragonal lattice with electric dipole. And this charges that you are seeing is divalent charges, Pb, barium, divalent metal ion, and this one that you are seeing is oxygen, and the third one, that smaller one that you see here, is the titanium, zirconium, smaller tetravalent. So typically this kind of structure, these are man-made structure, these are the structures that have typical piezoelectric behavior. So there must be some asymmetry in the structure that will generate, that will give rise to this kind of potential difference. If above the Curie point it becomes symmetric arrangement of charges, and there is no such charges will develop. So that is so above the Curie point there is no such thing that will be observed. Below the Curie point we will observe all this behavior. So net dipole moment will emerge. So this is something that we have already yeah, just like we talked about domains in magnetic materials, those were magnetic domains, and local alignment of electrons in a particular direction sorry, of dipoles in a particular direction, not electrons. So dipoles having a alignment in a particular area, they are pointing in one direction. In another area, they are pointing in another direction. So we can again talk about domains which are arising due to dipole moments. But overall, there is no net dipole. So as when they are randomly oriented, there are several domains where there will be collection of dipoles which will be pointing in one direction. There will be collection of dipoles which is pointing in another direction. So overall, in the material, there will be no net polarization. But when you apply, when you squeeze them or apply some pressure, they get aligned, and then you get to see this kind of behavior. So that is polarization, random orientation initially, then they get polarized when the electric field is applied, and even after the electric field is removed, some alignment of these things remains, so giving you overall net dipole moment. So this is behavior. So remanent polarization is the term that we use, similar to the term that we used for remanent magnetization. Okay, so remanent polarization and remanent is the term used over here. The application is immense: loudspeakers, microphones, guitars. So everywhere you have these piezoelectric crystals being used. I'm not going to. So even in your mobile phones, uses all these uses piezoelectric crystals. So they pick up the vibration. They are so sensitive that even when you speak, when you say something, so that vibration, sound waves, when hit the surface, it produces a compression or in that system, and that creates a signal, electrical signal. So we also have ferroelectrics, which is similar to uh, analogy with ferromagnetism, ferromagnetic. So whatever you have understood about ferromagnetism, everything is same, but the terms here are electric field E, and instead of here we have P, polarization as the thing, and instead of magnetic field we have E. Rest of the things behavior are same. So it is in the electric field, the behavior is alignment of things. So the dipoles are getting aligned, and you are having a high value of polarization, and it reaches a saturation value, maximum value of thing, when all the dipoles have aligned themselves in a particular manner in the material. So that is the saturation point, B and C. And when you reverse the direction and move along, you reach a point where, so this is the P, we call it PS, saturation polarization. Just as we were referring to saturation magnetization there, we are talking about here PS, and this point is remanent polarization. Here it is due to the dipoles, alignment of dipoles in a molecule when the electric field is applied. Okay, so remanent polarization P R, that's how we are representing it. And then you see the value of EC. So this is the coercive field. Coercive, so it is the electric field which is required to make the polarization zero. So these are ferroelectric materials which so saturation phase, saturation, selective side, positive side, increasing V, decreasing V. So this is a behavior so similar to so ferroelectric is something which will have a loop kind of thing. It will never go back its path of this one. And similar to paramagnetic, analogy is that of paramagnetic. Similar to paramagnetism, you can also talk of paraelectric. So below Curie temperature, they will behave as ferroelectric, and above Curie temperature, it will behave as paraelectric. So similarity between the two type of properties, one which we discussed already in magnetism, and the second one in this kind of polarization with electric field. So paraelectric, similar to what we are getting a straight line, and saturation occurs at very high electric field, and when you take a reverse path, it will retrace its path passing through zero. So there is no remnant polarization in case of a paraelectric, or in case of a paramagnetic there is no remnant magnetization. So this is a parallelism you can see between the ferromagnetic, paraelectric, paramagnetic. Only thing is that the field applies is different. The magnetic moment that we are talking about is different. Sorry, the moment is that of either magnetic dipole or electric dipole. So these are the things that makes it different. If it is magnetic dipole, we talk of magnetization. If it is electric dipole, we talk of polarization as the term to be used for discussion of this kind of behavior. So that's all. This takes finishes our. So that's the end of. So yeah. So now your solid state, most of the things are covered, and now we can